Okay, today I want to talk to you a little bit about Lab 8, which is in your lab book if you look at page 79, an introduction to topographic maps. The reason we're doing this is, generally speaking, when we go out into the field as geologists to map rock units and features, we use a topographic map as our basis. And generally speaking, most geologic maps use a topographic map as their basis. So this is to help you understand those maps and their use. I'm not exactly assigning the lab just yet. I have to, because we're now going completely virtual, I have to try to figure out how I'm going to get those particular pieces of the assignment to you. And I've got an idea on that, but I've got to get some materials together and create some displays for you guys to be able to download and look at real time on your systems. So I'm doing the lecture now. Hopefully by next week I'll have the lab figured out and set up on the online environment for you guys to do. So first and foremost, let's start with just the idea of a map. What is a map? A map is just basically a way of representing the three-dimensional world in a two-dimensional image. One of the things that matters with it is going to be, what are we looking at? What sort of system are we using? Ideally, the best way to display the Earth is going to be with a globe. But globes that are large enough to provide any real detail are physically impractical to use. So we have to represent the curved surface of the Earth on a flat surface of paper. So this also is going to create something that we don't need to get into too much here, but it's called distortion. Generally speaking, when you look at the surface of the Earth as a three-dimensional object, you can preserve the size, the shape, the angular relationships. When you flatten it out, you're going to lose at least one of those, and possibly two. So there are many different ways of doing what we call a projection, to project the curved surface onto a flat surface. We're not going to get into that. We get into that more into physical geography than we do here. Now, generally speaking, regardless of the maps that we use, the two-dimensional map that we use, it has some sort of system for referencing where you are at. If you've ever been to the mall, the map of the mall is usually a grid of numbers and letters sometimes. Sometimes it's blocks of buildings and numbers. Each section has a letter and each subsection has a number type of situation. Generally speaking, when we're dealing with topographic maps, we're going to be using some sort of an X and Y coordinate system, very much like you would talk about in algebra. So X is going to be our horizontal, Y is going to be our vertical axis. Now, generally speaking, there are two primary systems that we use and that we're going to use in this lab. The first of these I want to talk about is something called Township Range and Section. This is a methodology that was created back in the 1800s, used mainly in western states as a very quick way of delineating sections of land very easily and very quickly. It's very useful in surveying today, so it's still surveying. If you were to ever get into the field of real estate, you would find that a lot of parcels outside of areas that are within a platted subdivision are described based on what we call meets and bounds, which uses the township range and section to describe locations. So to describe it in township range and section, this is the state of Arizona, and it is divided. It has two axes in it. You have the principal meridian, which divides the state east-west, and you measure along in the north-south method. And you have the base line, which divides the state north-south and is measured in a east-west division. Anybody ever heard of baseline in reference to Phoenix? Think about it for a second. Hopefully, one of you just said, yeah, isn't there a baseline road? Yes, there is. And baseline road is the baseline for Arizona. So if you ever go on baseline road, you're on the central divider of the state. Now, instead of trying to draw this out for you, I'm going to reference the lab book off and on. But when you look at this particular grid section here, you have townships which are counted north and south, and you have range which is counted east and west. These are not quite the same as your cardinal points of on an x or y axis for algebra. You don't have 1.5 or 1.2 or 1.3796429. You have 1, you have 2, you have 3. Okay, and that's because in township, range, and section, you're dealing with a box, a 6 mile by 6 mile box. So every township is going to be 6 miles on a side. So it's 6 miles north. That would be 1. Then the next 6, from 6 to 12 miles north, would be 2. 12 to 18 is 3, so forth and so on. Same thing for east-west. 6 miles from 0 to 6 is 1 range. From 6 to 12 is 2 range, and so forth and so on. Now, we also do these basically north and south. So if we're counting north of the baseline, townships get a township blank number north. Townships south of the baseline get a township blank number south. If we're counting east and west of the principal meridian, it's range number, and then it's range blank number east or range blank number west. Okay, so we describe that out. So if I was to tell you that we were located in, say, Township 23 South, Range 12 East, that describes a 36 square mile area in the state of Arizona, which is over 1 million square miles in size. So with just 2 numbers, I've described a relatively small location. Now, if I was to tell you to try to find a specific person standing in that location, well, it's a little more difficult. Okay, 36 square miles, that's a lot of land for a single person to try to locate. So, what do we do about this? Well, it just so happens that each township range box is then itself subdivided into sections. And each section is a 1 square mile box. So we divide it into 36 boxes, just like this. And this is the way it's actually numerically arranged. So if we start in the northeast corner with 1, to the northwest corner 6, drop down, count, drop down, count in a zigzagging motion. So each box represents 1 square mile. So now if I told you we were in Township 23 South, Range 12 East, and Section 20, well, now it's a 1 square mile area. Hey, a lot easier to find somebody in a 1 square mile area than it is to find them in a 36 square mile area. But you can see how very quickly this process can describe a fairly unique location. Now, we're not done. We can subdivide the sections even further, because technically, if I'm trying to own some land, hey, yeah, it'd be great to own a whole section, but I can't afford it. So maybe I can afford something a little less. So when we look at how sections are divided, things change a little bit. We divide them in halves, both north, south, and east, west, to create quarters. And we divide each of those quarters into quarters. So if you look at page 82 in the lab book, there's a breakdown of this. So this would be 1 full section. And so this right here would be the northeast quarter of the section. So if I was to describe this location, it would be the northeast quarter of Section 20 of Township 23 South, Range 12 East. Now, here's the powerful thing about this. That also automatically tells me how much land it is. 1 square mile is 640 acres of land. An acre is a little over 200 feet on a side. 1 acre equals 43,560 square feet of land. We can look, and 1/4 section is going to be 160 acres. 1/4 of that is 40 acres. 1/4 of that is 10 acres, and so forth and so on. So we can keep doing this. We can also say that it's a north half, or an east half of something too. But every time we drill down smaller and smaller, we're looking at the next smaller division of quarters. Okay, so if I was to describe this section right here, okay, in the way we've been doing it so far, this would be the southwest quarter of the southeast quarter of the northwest quarter of the section. So the southwest quarter of the southeast quarter of the northwest quarter of section 20, township 23 south, range 12 east. Makes sense? I know it's a lot to throw at you, especially in this environment, because I'm not drawing it out as I would normally do in the classroom. But it gets very powerful. You can go down usually about 1 more, and you're at 2.5 acres of land. That's usually about as small as they would get. So you could have that you're dealing with the northeast quarter of the southwest quarter of the southeast quarter of the northwest quarter of township 20 range, township 23 of township 20, 23 south, range 12 east. This allows us in large tracts of land to very quickly and very easily locate where something is through fairly simple methods of survey work or just reading a map. One of the aspects you're going to be doing which is what I'm trying to figure out, is I've got to get a map that has township range and section on it. I'm going to have different locations on it, and you're going to identify what those locations are based on that. What I have to do is I have to come up with one that's going to be readable to you. I normally have maps that I have copies of in the classroom. Obviously, don't exactly have access to those anymore, so now I've got to come up with something that will work in its stead. Okay? Make sense? I hope so. Another way of dividing the Earth up is in what we call longitude and latitude. Now, longitude and latitude is a much, much more precise method. Instead of locating a area, which is what township range and section does, longitude and latitude locates a point on the surface of the Earth. I'm going to try to describe it here. So, if this is the Earth, and this is the Earth equator. That was a good one. Equator. This is the equator. That means we're up here. We're going to have the North Pole and the South Pole. Okay? So, latitude and longitude is looking at arc measurements or angular measurements on the Earth based on the relationship between different points on the surface of the Earth to the core of the Earth. Now that seems a little long-winded of an explanation, but I can make it look easier for you. So let's do a cutout of the Earth. And I'm going to draw the equator as a dashed line and the line between the poles as a solid line. Okay? For latitude, latitude is the angular measurement above the equator, referencing the center of the Earth. So if you were at a point about right here, which is about halfway between the equator and the North Pole, you would actually be at approximately 45 degrees north latitude. And that would be because the angle between the North Pole and the equator is going to be a 90-degree angle. And if you're bisecting that angle perfectly, then it's a 45-degree angle. So this angle right here would be 45 degrees. Okay? And that's how we measure latitude. We measure it basically as an angular distance or an angular measurement from the equator towards the pole. So it's north or south latitude. So the equator is going to be 0 and the poles are going to be 90 in each case. Okay? Now, depending on the style of reference you wish to use, the North Pole would be 90 degrees north latitude and the South Pole would be negative 90 degrees latitude, or you can just say it's 90 degrees north latitude, 90 degrees south latitude. Depends on your preference. Okay. What about longitude? Longitude's a little bit different. Instead of being an angular measurement from the equator, longitude is an angular measurement from a specific reference point. And this caused problems in the past. It used to be that different countries created their own prime meridian. The prime meridian is the 0 line for measuring longitude. This caused some problems. Namely, it caused some problems between two countries of Portugal and Spain. Portugal and Spain got into a fight because when they discovered the New World, i.e. South America, they decided that they would split up this based on everything beyond a certain angular distance being owned by Spain and everything on the other side being owned by Portugal. Well, depending on whose prime meridian you took, that gave more or less land to one or the other. Needless to say, war was fought over this. It wasn't until last century, basically, that it was standardized for the world. And now the prime meridian for the Earth, what we call 0 degrees latitude, runs through Greenwich, England. So, the 0 line, I'm going to put up on the first one as if we're looking onto it. And so we measure then the angular distance around the circumference of the Earth, or the equator. And what that does, though, is that creates lines that might look vaguely familiar to you. Like that. Where it kind of looks like a basketball. Kind of. Not really, but kind of. Okay? So these would be lines of longitude. Now, the interesting thing about the Earth in terms of its geometry is that the shortest distance between any 2 points on the surface of the Earth is what we call a great circle. That's going to be a circular line, or a circumference around the Earth that encounters the entirety of the surface of the Earth and would include the center of the Earth in the plane that it creates. So if you want the fastest way between any 2 points, you would travel a great circle route. This is why some airplane routes look really funny when you look at them on a two-dimensional map. Like they're going way out of their way north to get to someplace else. That's because they're actually following a great circle route, which is much shorter, much quicker to actually travel than if you were to try to fly what would appear to be a straight line on a flat surface. So we measure longitude in terms of degrees east or west of the prime meridian. Eastwards is positive, westwards is negative. So we actually are at about minus 111 degrees minus 111 degrees longitude, or 111 degrees west longitude. So, how good is this system going to work? Well, at 1 degree by 1 degree, that's a pretty large box. That's 40 some kilometers on 40 some to 60 some kilometers on average, depending on where you're at on a side. So it's a big area. So we need a smaller division again. Now, instead of doing it in quarters or something like that, we do it a little bit differently with degrees of angular measurement. So 1 degree, which we denote by the symbol, the little circle symbol, superscript, is going to equal 60 minutes. Yeah, 1 degree is 60 minutes. Okay? Why does that work? It just does. I'm not going to get into it, but it actually has to do with measurements of how the Earth is moving through time along its rotational axis as its origin. It goes back to astronomy. A couple of thousand years actually back. It was either Mesopotamians or the Babylonians. I can't remember which now. But 1 degree 1 minute equals what? Points to the person that said 60 seconds. Okay? So we measure latitude and longitude in degrees, minutes, seconds. Once we start measuring with seconds, we can get to be very, very accurate. There are some GPS units out there you can buy today that are not that accurate by survey standards, but they'll still get you within 10 to 15 feet of the actual location on the Earth. So they're pretty accurate. There are some that are survey grade. They will get you to within a fraction of an inch in accuracy. So we measure by degrees, minutes, seconds. So we could be at 111 degrees, 30 minutes, 54 seconds as a point. Okay? Now, when we look at working with this on a map, again, I'm going to ask you guys to locate those same points that I'm going to ask you to do Township Range and section on. I'm going to ask you to do longitude and latitude also. So I'm going to have that same information on there. There's 2 ways you can do this. Now, generally speaking, we'll get to this in a moment. You got to understand the scale of the map in order to figure this out. But generally speaking, one of the things you can do is if you have known reference points on the map. So let's say this says it is 0 degrees, and this says it's 0 degrees, 15 minutes. What you can do is you can actually measure that, create a scale for it, and then you can figure it out yourself, mathematically speaking. It would basically be, I could do it as D1, DO. So it would be, if I measure from the 0, it would be 0 plus the difference, D1 minus DO, divided by this distance, X. If I'm going to that point, X1, so we'll call it X naught. So X naught times X1 will give you actually the number. It's a fairly simple mathematical ratio. If you don't understand math, if you don't understand algebra, understand that it's going to be a little harder for you to do, but basically it's just a relationship between distances. Okay? It will work in the y direction too. You just have to keep in mind where you're measuring from, what your measurement basis is. Okay? The other way to do it, I like to call the eyeball method. Okay? If I know what this is, I'm pretty close to half right there. What's half of 15? 7.5, so 7 minutes, 30 seconds. So that I'm a little bit above that, so maybe call that 7 minutes and 32 seconds. That might be good enough. It's enough to get you in the ballpark. The idea on this exercise, when you get to it, is not to put me standing in the exact correct position. I just want to be in a position where if I go to where you say and I turn around, I have a reasonable chance of seeing the object or the location you're supposed to be describing in terms of its spatial reference. Does that make sense? I hope so. Now, that means that we also have to understand then the scale on the map. Scale is how we reference the real world to the display that we have. Okay, so scale matters. Now, here's the problem. Scales can come in four different forms, as as your lab book shows you. There's a bar scale, which basically has a physical bar on the map, and then it has notations of what distances are. You can have a fractional scale, a fractional scale, which is basically a fractional representation, 1 divided by whatever number. You can have a ratio scale, very similar to a fractional scale. It's 1 but with a colon and then another number. And then you can have an actual scale, which says, 1 inch equals 1 mile on the map. The 1 inch equals 1 mile is helpful in some ways and not helpful in others, because if you're trying to do measurements on the map, 1 inch equals a mile, that's great, but now I got to figure out what fraction of an inch does to a mile, and so forth and so on. So generally speaking, we use a numerical scale, and numerical scales end up having to be what we call unitless. And the reason for that is we want to make it so that 1 unit of whatever unit of measure we're using on the map will represent a specific number of that same unit on the ground. So let's take the example of 1 inch equals a mile. Okay. Well, inches and miles are not the same units of measurement. So in order to get that unitless, we have to change the units so that the units are the same. Make sense? So if the units are the same, the units essentially cancel and we become a unitless system. So 1 inch equals a mile. Which is going to be easier to convert here? I'm going to say it's easier to convert a mile to inches than to convert an inch to miles. So let's go with that. So how do we convert a mile into inches? Well, we just have to look at how we convert that distance. So 1 mile equals 5,280 feet. So now we have 1 inch equals 5,280 feet. We're a lot closer. 1 foot equals 12 inches. So if we multiply 5,280 by 12, we then end up with 1 inch equals 63,360 inches. Hey, inches and inches. Inches cancel out. We're down to 1 equals 63,360. And that becomes our scale. Okay. Now, one of the confusing things about scale is large scale versus small scale when we're looking at these numbers. It has to do with the value of the ratio or the value of the fraction when we do it. So a small scale map would be a map like 1 inch equals a mile, because 1 inch equals 100 feet would be a larger number. It would create a larger ratio, therefore it's a larger scale map. So when you do the process of the lab, one of the things that you're going to have is some questions regarding scale. And you're going to be asked to take some scales that are given as actual scales and draw a bar scale, come up with the correct fractional and correct ratio scale, which are going to be the same thing, and just get those numbers together. Okay. In fact, actually, questions 1 through 3 in the lab book, you guys can actually do as soon as you're done with this, if you wanted to in the lab book to get done. The rest of it is what I've got to put together. Now, I said we're talking about topographic maps. So far, I haven't even mentioned the word. What's a topographic map? A topographic map is a very special map because not only does it give us the X and Y of where we're at on the surface of the land, it gives us the Z value of the land. So it actually represents the vertical changes in elevation on the land. Basically, a way to think of it is if you imagine a three-dimensional hill and you have a plane cutting through it at specific intervals. Everywhere it where it touches that plane, we create a line. Or where that plane intersects the surface, we create a line. Okay? Now there's some rules about these that we're going to have to follow. And they're fairly simple. So keep in mind that first and foremost that a contour line, which is a topographic line, we call them contour lines. A contour line is a line of equal elevation. So if you walk that line, you will ultimately end up right back to where you started. They always close on themselves. You will not go uphill, you will not go downhill. You will stay at the exact same elevation. Therefore, contour lines never cross. They always close on themselves. The slope of the surface we can tell by the relationship of the contours. Think of it this way. If the edges of the book here and here are two different contours, well, if they're like this, they're further apart on the map. If the surface is like this, they're further apart on the map. If they're like this and we're looking down at it, they're closer together. So the further apart the contours are, the gentler the slope, the flatter the land. The closer together they are, the steeper the slope, the steeper the land. The highest point of any feature, or the lowest point for that matter, is usually going to be circled by contours. We have a rule that we call the rule of V's that works very well with contours, and that is when we are dealing with structures, if we look at where we get a V shape in the contour, or upside down an A shape, that can tell us something about the land if we pay attention to the directionality of it. If we get a V that points uphill, that tells us we're dealing with a valley. If we get a V that points downhill, that tells us we're dealing with a ridge. So we can actually begin to read what the surface of the earth looks like without having to actually see it. Now, every fifth contour, every fifth one, is going to be a different color or a darker color, or it's going to be a thicker line. We call these index contours. So every index contour will tend to be labeled with its actual elevation above sea level on it. Generally speaking, this means that we can always figure out what our elevation is within about half the contour interval. So if I have contours that are set up to be 2-foot contours, that means the distance between every heavy line, or every index contour as they're called, will be 10 feet. So if I have 0, I'll have one line, that's 2. Another line, that's 4. A third line, that'll be 6. A fourth line will be 8. The next fifth line will be a heavy line again, and that will be 10 feet between. Or if we know any two index contours that are adjacent to each other, we can figure out what the contour interval is. The contour interval is the actual vertical distance between each contour. So in the case that I just used, it would be 2 feet. Unless otherwise marked, there will be benchmarks on the map. There are little X's that will have a number listed with them. Those are actual elevations of a specific point. We usually use these to help us understand what's happening below the surface of the Earth, because we can see how different things are expressing themselves at the Earth's surface, how different layers are exposed. And we can use this to a degree to help us understand the structures under the Earth. And we're going to get into that in the next lab and in the next lecture when we talk about structures, but I'm preempting that right now just to talk about the contours. Now, one of the things I'm going to have you do also, and I'm trying to figure out how to do this in the lab final, I got an idea, but I'm going to have to hold off on that, is something that we call a cross-sectional view, or a profile view, topographic profile. This is a way of looking through a three-dimensional structure in a 2D plane that would be a vertical cut through it. So how do we do that? Well, in a way, it's actually fairly simple. I'm going to explain the process. It's in the lab book here. I'm going to explain it hopefully you'll understand it. So, here's a topographic map. Okay, got a little stream valley, 2 hills. Okay, so here's the rule of V. So the V is pointing uphill, so that tells us that this is a stream valley. Not to mention I've got a symbol here of long dash, 3 dots, long dash. That's actually the symbol for an intermittent stream. So my profile view is going to be between these 2 points of A and A prime. So how do I create this? Well, this is how I normally do it. 1, I like to use graph paper. This is your friend in doing this, okay? What I like to do in general is I'll fold the edge of the graph paper to get the edge of the graph and put it right against this line. And then I will make a tick mark at every point where the contour intersects this line that I'm interested in. I will also tend to label them in certain ways so that I know which one I'm dealing with. Okay. Once I have that, I can then take and go down, and I have to have my setup down here. Now the X scale on this is going to be the same as the scale on the map. No problem. The vertical scale, that's got to be different because it has to be exaggerated. Because if we have it at the same scale as the map, usually it's going to be so flat you're not going to see anything. And while that can be technically correct, it will not be considered actually correct. So please don't try that. So what I like to do, though, is use a straight edge and just bring down, and I did it here by marking lines in this case, dashed lines. Bring it down until it gets to the proper intercept or elevation point on the grid paper, and I make a dot. Once I have all the dots in, it's a matter of playing connect the dots. It's very simple. It's tedious, okay? Generally speaking, one of the things I do with this lab is I give you guys 2 copies of the same area with the same line on it to do, what with different topographic intervals on it so you can see the difference. I'm going to think about how to do that. I still want you guys to have the practice of doing this and get that feel for what we're doing, because when we start looking at the block diagrams that we're going to be using for geologic structures, this kind of gives you an idea of how those are actually envisioned in the first place. But with that, I'm going to cut it off here. Like I said, I'm not assigning the lab right this moment today, which is April 1st, although that could be an April Fool's joke. Damn, I should have thought about that earlier. However, please go ahead and read Lab 8. Go ahead and start working on this once you get the other labs turned in. Again, I'm not assigning it officially yet, but you're going to want to get started on it soon. And keep your eye out for the lectures for the next chapter and the next lab, because as soon as I do the structure lecture, probably do the geologic structure lab. With that, I'll bid you a fond adieu. I will see you guys in what looks like to be a couple of hours for tonight's class. Again, we're going to try to keep it short so you have the time to be able to watch these videos. Take care.